Welcome to Industrial Applications Level 2, and this video is on interlocking logic. With traditional electric three-phase motor starters, there are two coils, one for forward and one for reverse. These can activate and energize a motor. These starters cannot be assembled with spare parts and are manufactured with built-in mechanical preventers or interlocks that prevent someone from jamming in the relay in the other direction. Across the top of this model are flat phase bars that changes two of the phases to obtain a direction change. There are two sets of auxiliary contacts that can be used to initiate a direction change, as well as a set of normally closed dry contacts mechanically bound to the overloads, such that when one of the overloads is tripped, the contacts will change state. Due to lower overall costs and versatility, variable frequency drives are replacing traditional motor starters. Changing direction is now simply a signal. Unfortunately, they do not have built-in interlocks, and so the signal must be interlocked at the PLC or signal source level. Once sent, the phases are switched electronically, and the overloads have been replaced with internal current and temperature sensors to protect the motor. Since they can alter speed, they often have analog connections to allow for speed reference changes, and they come with their own auxiliary contacts. Some models have Ethernet capability, which means signals can be sent and received simultaneously and at a high rate and reliability. In our first example of interlocking logic, we're going to use and start with the 3-position switch that's on the trainer. So the 3 positions that it has is 0, 8, nothing, and digital input 0, 9. So we're going to put a couple of contacts on here. And interlocking is not strictly reserved for motor control. There can be program selects that you do not wish to have. So what I'm going to do is I'm going to start with a rung that has our 2 inputs, and this will review the intent that we're trying to accomplish with these interlocks. So we're going to rename that and I'm going to call this manual select. So when I have manual select, I'm going to turn on an output, and that's going to be my manual mode. Or manual operation. So my next rung, I'm going to do the same thing, and I'm just going to grab a couple of contacts here and a coil and create another rung below it and a coil. I'm going to make this one a knot, and this one I'm going to go and use another input 9, and I'm going to rename that automatic mode. So in between these two, when I go from the switch position over to the next position, there's going to pass through a center section where there is nothing. So I'm going to select 2 of these not conditions. So when it is not our first, pardon me, our first position and it's not our second position, then I'm going to create a new output, and I'm going to call that one no mode. Neither where I am neither in automatic or in manual. And on this other one, I'm going to call it automatic. So it's straightforward that the switches are doing the interlocking for us. We cannot be in one condition without the other. But one of the problems with this is if I simply have that surface selector switch, given an industrial environment, things are moving, people are walking by, it's quite possible that somebody can brush against that switch and inadvertently take it from the automatic to the no mode position, or maybe even take it over to manual. Or if someone is in the manual position and they're working upon it, the same thing is you do not want that situation where they accidentally hit it and put it into automatic, because that can result in a very dangerous situation. So what we're going to do is we're going to interlock these with another contact, an internal contact that says I'm going to enable one of these. It's one of the other push buttons that says I have selected manual mode, and I've pressed the button to acknowledge that I'm in manual mode. Once that happens, the other ones cannot be done, because I'm going to put the not manual mode select and not automatic select, etc., in the other ones, so that you cannot, unless that's taken out and manual mode is defeated, you can't accidentally brush that switch and change the position of it because it has not been initiated. So I'm going to put in another contact. Okay, so let's add a comment or direct contact to each of our rungs, and we're going to use one of our digital inputs. Enable push button. Okay, so if I'm in manual, I'm going to put the selector switch over. I'm going to press the enable button. That's going to turn on my manual mode output. But I have to seal in, because that enable bit is not a maintained contact. So I'm going to have to put a branch around that, and I'm going to take the manual mode to seal that in. Now, once I've done that sealed in, if I lose this, that should drop that out. But I'm going to put some insurance, because one of the things that you do when you're programming is it doesn't hurt to go a little bit overboard. Simply by putting in interlocking contacts, you make it harder and harder for somebody to accidentally or inadvertently change a particular state. So manual mode is still good, but before that seals in, there's no possibility of it being put or switched into automatic mode. There's no possibility of it being dropped into no mode. It ensures that only the manual select and the manual mode have been done. All of these are real world inputs and outputs. So there's the possibility of the inputs being locked on, which we'll cover in a much later class. But this way gives us the maximum amount of insurance that this cannot be mixed up for anything else. It is a deliberate act. So I can do the same thing with these other branches. I'm going to have my enable mode, and I'm going to put in these same contacts again. Put another branch around the other one, and I can just go one, shift, 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 Control C, copy, boom, done, Control V, boom, done. Now I don't want this to be manual mode, I want this to be no mode, so I just have to change that to 08, and I have to change this one to 07 to get my auto mode. So here we have a simple method of interlocking. We're still using a mechanical switch, which in the case of a motor, you'll have those jog switches that mechanically will disengage the motor and then put you in a neutral state and then push it into the other direction. Those can have limitations simply because you're swapping the fields very quickly. May not have enough time for the motor to shut down or slow down, and also they're for very small motors, simply because of the amount of current larger motors, and especially larger voltage motors, will draw, and you don't want to start opening and closing contacts, especially when the motor may be still moving in a direction and be sort of self-generating, as it were. So this is simply one form of interlocking, using that interlocking switch to enable us to have 3 different types of operation, and there can be lots of applications for this. Okay, so now we're going to make a couple of rungs that are interlocked forward and reverse, so that you press one button, it'll run. If you want to go the other direction, you press the other button and it should change. There's variations on this that we'll get into when we get a little bit deeper into forward and reversing starters. So the first thing we're going to do is we have our blank rung, pardon me. We're going to make 2 of them. I'm going to grab 2 outputs. I'm going to call one of them forward. I may have already used this one. No, let's go with that. We'll call that one reverse, and we'll do that one as forward, or make this one forward and the other one reverse. And you can reverse engineer any rung. You don't have to do it necessarily from left to right. If you want to start with your output, oh, that's odd. I guess I didn't pay attention. And let's start digital work 5. Yeah, I did that. Oh, okay, there we are. Okay, so we're going to do some preconditions. First of all, we're going to put a normally open contact, and we're going to call this one our stop button, and our stop button, because it never doesn't matter one whit if you can get the motor to start. Can you get the motor to stop? Then we're going to put in our 2 push buttons. That's our digital output. So let's find an input. We're going to use enable, doop, doop, doop. Okay, so we're going to use, that's 0, 1, and 2. So we're going to use digital input 2 for our forward. And we're going to rename that. While we're here, we might as well rename this one reverse. Darn that cap box anyway. So there's our forward. Doop, 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 doop. in our reverse. Push that, it's going to go forward. Push that, it's going to go to reverse. But I don't want to be able to push them at the same time, so I'm going to put my blocking strategy. And the blocking strategy simply says I have two different choices here. I can use the push button. So when the push button is not pressed, then it's going to allow that to go through because I'm using the examine if open or examine if off condition, and it's going to allow them to put it forward, and the same with the backwards. But it's often better to put as much insurance as you can afford. So let's put on one of them our digital output, and let's put our digital output in the opposite direction. So if it's already running in forward or already running in reverse, I cannot put it in forward, I cannot put it in reverse. This also means I have to look and examine at my push buttons. So I'm going to look at when I press my forward, I don't want somebody who might have jammed in a push button with a tie wrap, and yes, I have seen that. I don't know why they would do it, but somebody's done that. So I'm now looking to say that in order for me to get it to go forward, the stop button must not be pressed. The forward button is pressed. The reverse push button is not pressed in at the same time, so I can't press the two buttons, and I can't have one jammed in, and I'm not already running in reverse. So all of that gives me permission to go forward. Now all I need to do is to put a branch around our forward push button and allow that once the forward coil is turned on, it will seal in. And I've done the same thing but with the opposite state. So to get reverse, the stop button has not been pressed, the reverse push button must be pressed. The forward push button cannot be in the pushed in position, they can't be locked in, and I can't be running forward. So when I press this push button, this is not going to open up, but this is. So when I press that button, that will open up the other push button. It'll change state because it's opposite. It will drop my forward and allow me to go into reverse. Once that's done, this then becomes false. So, it becomes active because it's no longer, this is false, so therefore this is true, and allows me to go into reverse. So I'm going to put in my branch, and I'm going to put in my contact, and I'm going to push in reverse. There it is. And I've just made two interlocking rungs so that it can go forward and reverse. All of this logic can be applied to any two-state solution that you require a 1 or a 0, an opposite state condition, whether you want it to be manual and automatic, the forward or reverse. If you have cylinders that do an elevator, there's up and it's down. Whenever you don't want an ambiguous state or the activation of two at the same time, you use interlocking contacts to accomplish it.